I3C work group. So let's dive in. So today I'm going to give everybody a quick introduction on I3C and I3C Basic, talk about a little bit of the power and energy performance improvements that this technology can present. And then we'll dive into more of the details of the I3C bus transactions and get into some additional resources. And then just as Dervla talked about, we'll do some Q&A at the end. Okay, so as an introduction, why are we talking about MIPI I3C? Well, as many of you know, the sensor market is growing tremendously, not only in the amount of sensors, but the capability. Sensors are getting smarter. We're not just dealing with thermal sensors anymore, but you've got gyroscopes, accelerometers, and more sensors in your devices. And of course, IoT is bringing this even faster. And so I3C was created by the MIPI Alliance as a cost-effective interface to help address some of these growing industries. So I3C, it targets mobile and IoT devices. It's built as a lower power, low pin count for high-speed communication, which is ideal for these IoT markets and these small form factor devices. Another big part of it is that it provides some compatibility, backwards compatibility as well with I2C devices. So let's talk about the I3C interface ecosystem a little bit. If you look at the left with our specifications, there's the I3C version 1.1.1. This is our version that's available to MIPI members. There's also an FAQ, app notes, and this was just recently released. So this is our full specification. Now, in addition to that, we also have our I3C Basic, which is a subset of the full version. It is publicly available by complying to the MIPI IPR, and it was also just recently released. So this is more of our public version that's available for everyone. We also have a lot of support in the ecosystem as well with our I3C HCI, our host controller interface, another publicly available open source piece of technology that allows connection to peripheral devices and application processors. We have the CTS, which is our conformance test suite. This was put together to allow people to come in, test their devices, be able to make sure that they're running in parallel with what everyone else is doing. So testing is such a huge part. We actually have interop workshops that we're hosting as well as part of our ecosystem, just to go out and help to better the developers and help the architects get through some of the complications of building a new system. We're also integrating into all sorts of different technologies, from debug to disco. We've got JDEC has picked up I3C for its serial presence detect and DDR memory. The DMTF is using the I3C transport for MCTP binding specification, as well as ETSI for its SSP platform, and plenty more to come that we're working on. So the I3C interface ecosystem is already rich. It's growing, and we have a strong work group that works very hard to keep it moving and keep it updated as well too. So key features. I3C was based on a fast and efficient communication channel. If you've been around since I2C, that was even some of the thoughts back then, but I3C makes it even better. So key features, it's a multi-drop 2-wire interface, max clock rate up to 12.5 megahertz. Also different voltage ranges that can be supported. On top of that, there's some optional features that allow for not just a standard data rate, but a higher data rate. We also have added optional support for multi-lane. So if the two-wire interface just isn't enough and you need access, there's optional support features to add that in. On top of that, we've added things like hot join, device reset, in-band interrupts, all sorts of different features to help system designers and help keep this bus as efficient as possible. System management, right? There's the ability for both primary and secondary controllers. Dynamic addressing, including group addressing, which is great. It allows um, a device to address multiple devices at once instead of always having to address each device individually. Can be great for efficiency. Um, and then, of course, backwards compatibility. I2C is a very prolific technology, and we don't want to leave that behind. And so we've presented ways to include backwards compatibility and be able to have mixed buses with this I3C technology. So that's a kind of a quick overview. There's a ton of information. There's tons of features surrounding the I3C bus. Of course, the specifications will go into full detail on all of those. So being that we're here talking about IoT, power and energy performance is key. And we've worked hard to make sure that those are improved upon in I3C. So why do we need it? Well, we know IoT devices are typically low voltage operation, many of them running on battery. Many are non-chargeable or non-rechargeable, and so low energy consumption and power efficiency are very, very important for the ability of these IoT devices to work for long periods of time. I3C solves that by including our excellent bus electrical characteristics. We handle both synchronous and asynchronous events, and segmentation is another great way to keep all of those low energy and power efficiency ideas going, right? And so moving on, here's how we do it. So I3C bus, simple two-wire interface. It keeps the component count down, low capacitance, and then the operating voltage. So we use a range. We know that out there in the real world, and we're not all operating at the same voltages. The traditional 3.3 volts is getting harder and harder for systems to meet, since the size and the processes are getting smaller. The voltages are having to come down low, and we've made changes to be able to accommodate that. On top of that, bus transaction operation. We worked hard to make sure we're minimizing the energy that's used per bit sent, using a push-pull driver whenever possible. And we also do well to manage the bus idle conditions, bus available conditions, a lot of bus management to make sure that we're being as efficient on the bus as possible, and that we're conserving power when we don't need to be using the bus. So if we look at some just figures here, um, energy-wise, we wanted to show, as far as a 1 kilobyte transfer, how the savings are for I3C versus the other technologies. So on the top here, we can see the energy to transfer 1 kilobyte. For I2C, somewhat high, whereas when you get into the I3C, you can see the HDR, TSP, HDR, TSL, DDR, and SDR. These are all different uh, ways that I3C can go about sending data across the line, from standard data rate to double data rate to high data rates. You can see with HDR TSP, which is a ternary mode, we can see 18 times lower energy reduction versus I2C. And at the same time, we're moving data faster. And so with that same HDR TSP, we're moving 33 times faster than what an I2C bus would be moving that 1 kilobyte. So huge improvements in both energy and the time for transfer with I3C. Another big part of it, like I spoke about earlier, was improving idle time, making sure when we don't need to be using the bus that we're not, and that we're keeping the power low. And so I3C has a CCC that it's a command code that is implemented to enter into these activity states. And depending on which activity state you enter into, depicts the amount of idle time that you can be in within that activity state. And so depending on the system and where the bus is at, if you know you're going to have a long idle time, we can enter into an activity state. This allows the lower power, custom power savings, and much better efficiency for your system. In-band interrupts. Another addition that we made allows for asynchronous data acquisition. So in traditional systems, a lot of time what you would see is you would have a host going out and polling and polling and polling, always sending polling for data, which could fill up the bus pretty easily. And so with IBI, we allow targets to asynchronously send an interrupt and let the host know, hey, I have some data that I need to send to you. The host can then say, okay, give me that data, and the data can be exchanged without the traditional inefficient polling mechanism. So the IBIs have been a great addition into our features here for I3C. Lastly, we have bus segmentation. And so we talked about the fact that the I3C is compatible with I2C. And so we won't dive into the full details of that, but due to the use of a spike filter, we're allowed to have a combination of a mixed I3C and I2C bus. However, not always the most efficient way of doing things. And so there's also options for things like a routing device, which would allow bus segmentation. And so we could have all the high activity data producers on one bus, whereas you have the lower activity on another bus. And by using our activity states, power savings, things of those sorts, segmenting like this can do great things for improving on power efficiency and overall system efficiency as well. So this is a great feature that be highly useful, I believe, for the IoT system. Okay, and there's other features as well. I would encourage everyone take a look at some of our supporting documents, go through our spec. Between hot join, device-to-device tunneling, timing control, many other features that have been added into our specification with designs like IoT in mind. I3C is always aimed to be that low power, low pin count technology, and so we've built it to support the technologies that use such a device. So that's the basics of I3C, and then for the in-depth transactions, I would like to bring on Michele. He's a IoT expert and a huge member of our MIPI I3C ecosystem. So without any further ado, Michele.
Yes, hi, thanks, Tim. Let me start the video so you can see me. Hi, everyone. So I think in the second part of the webinar, we look at a couple of examples, some use cases in more detail, so you get a chance to perhaps understand better how the good power performance is achieved. So we just picked a couple of examples because the time does not allow to really go And as Tim just said, there is also tons of other possible uses. But okay, without any further ado, let's jump to the first case. So before I describe the say the anatomy of a bus transaction, let me remind, or actually this could be new for some of you who are not so familiar with the I3C. What are the electrical states, the bus driving can be? There are essentially four states. There is usual open drain, which will need a pull-up resistor or an active pull-up, which is, I would say, well, it's needed in some cases, and it's also there because of the I2C compatibility requirements. But not only that, it's in some cases you need to arbitrate the bits and so on. So that's the way to do it. Of course, if you are receiving data, you will be in high impedance mode receiving in data. And as Tim mentioned before, we whenever possible, we like to switch in push-pull mode, which is much more efficient way to send the data across the line. And then finally, there is a fourth mode, which is referred as an I-keeper. This is really a pull-up with, a very weak pull-up. And this has happened that we need to be used in some special cases. I will tell you in a second when that is used. Let me say now about the two lines, the SCL and the SDA lines. The SCL line in I3C, it's, let's say, always in push-pull mode, and it's always driven by the controller. The reason we say they're almost always is best because in I3C you can the controllership can be transferred from one controller to another. You have initially a primary controller, then a target can request to become a secondary controller. So there is a time when you handing over this where there is really a very short time where there is no controller driving the line. So in this time, really the wire could be floating, and this could induce some spurious transition. So that is why it's recommended that one keeps the high keeper that ensures the stability during the controller handover from one device to another. So other than that, I think the SCA line behavior is fairly straightforward. STA line, however, is much more complex than that because you can not only can switch from some open drain to push-pull IZ, but it can also, depending on where the bus transaction sits, it needs to be driven either by the controller or by the target. If you're doing a read from the target, you need the target to be able to send the data out. So this is, compared to I2C, it's probably a much more complex behavior, but that we'll try to optimize how this is done. Okay, so this is sort of the introduction on how the wires are handled there, sort of the analog front end. Now, what are the sources, at least from an electrical point of view? What are the sources of energy consumption? Okay, on the open drain, it's fairly straightforward. When I have the line is low, to keep it low, I need to draw current from the pull-up. So the longer I stay low, the more current I draw. Not only that, this also slows down, the open drain slows down because of spurious capacitance. So the message there is that we try to design the specifications so that the open drain mode is kept to the bare minimum, really, when it's necessary. Second source of power consumption here are the spurious capacitance, where the capacitance can come from the wire or from the input capacitance of the I/O pads. The wires depends on the design, of course. How long are the wires? How close are to the ground plane, and so on. And the input pads, this will depend on the technology that the system designer will choose. But overall, the message is that every time I need to bring the line from low to high and high to low, I need to charge and discharge those capacitance, wasting energy. So in some cases, we try to minimize the transaction. Less transaction, less energy. And for example, the double data rate that Tim showed before, when we showed the performances, in the double data rate, you are sending 2 bits per clock. So you're halving the number of transactions of the SCL line. So you're saving energy there. So it's not only faster, but it's also more efficient. By the way, there is also a third source, when the drive stage is switching from high to low or vice versa, there is always a short overlap, between the upper PMOS and the lower NMOS. Okay, modern technologies, this overlap is really being greatly minimized, but however, there is still some shoot-through current, and this is causing, just energy waste. And so the message here is, again, let's try to minimize the number of transactions you do on the lines. Okay, so this is sort of the electrical, let's say, introduction, and let's look now at the typical transaction. So we always start with both the SDA and SCL lines high. That can, as Tim shown before, this can be in bus idle mode, bus ready, but we always start with the two lines low, and they have the start sequence, SDA, and followed by SCL going low, similar to the I2C. And then in I3C, it's almost always, except few instances, we put up the 7E address. So this is a 7-bit address reserved for I2C. This is not recognized by I2C devices, so they will not respond. As you notice, out of the 7 bits, 6 are high, which means they were not consuming energy. So, and this is a small detail, but I think that this is repeated, along the life of a product, probably millions of times. So it really adds up. So at the end of that, there is an indication bit whether it's a read or a write. In the example here, it's a write. And then if there is at least one I3C target, they will acknowledge the broadcast address. And then at this point, you see that the color changes from yellow to blue. Here, yellow is the open drain, say, state, and blue is the push-pull state. Then both lines now, SCL is always in push-pull. We can go at full speed. Don't need to worry about the slow race time of the open drain. And so you're going faster, more efficient. Going faster is also keeping, when you have data moving, you need to keep peripherals running, maybe CPU running, and so on. So it's not only electrical part, it's also, let's say, the logical part that you're saving energy there. And then in the example here, then you on the acknowledge bit, you go back to open drain. So with the clock, you need to slow down again and then go up again. So this is sort of the dynamics of the transaction. Maybe a bit of discussion is deserved from the clock line. You notice here that during the reserved address, the low part is much longer than the high part. This is because of you need to account for the slow rise time. And then, but then the upper, the high time, how long should that be? There is an important feature related to I2C compatibility. Basically, I2C devices will ignore any signal which is below 50 nanoseconds. This is known as the as a spike filter. This filter can be also present sometimes in I3C devices. So you will need to, depending on the behavior of your application, you might choose to keep this clock very sharp, below 50 nanoseconds. This becomes completely invisible to the I2C, as long as the I3C devices can see it. So it is, but the idea is there. So if you have I3C, you remove spike filter, you can go fairly fast. And then when you go in push-pull mode, you move even faster. So this, okay, so with this description in mind, let's go back to the diagram we saw before, in segmenting a system into a high activity and a low activity bus. You understand, I think, better now why is a good thing to have a pure I3C bus. You don't need to worry about all this compatibility. You can run much faster. And so put all the I3C typically sensors on a separate bus, which will be can be made even shorter. So you're saving energy by reducing the capacitance of the wire. Probably, okay, you have to have maybe a secondary controller with an MCU, but this is usually there because very often you are acquiring sensor data. There is some processing that needs to be done, like filtering, sensor fusion. So it's something that probably is already there. And also the routing device, if you have an MCU with a double interface, actually MCU could perform also the routing function. So it's really not big penalty, but the gain is fairly good in terms of efficiency. Keep in mind, I think in modern products, sensors now are spitting out data at several kilohertz level. So it's really a fairly high activity, and keeping that kind of well managed, it's important from the energy point of view. So here, let's just build up a sequence how this would happen. Basically, you are everything is sort of in the, let's say, the high activity bus in a rest mode. Then the MCU periodically on a certain, let's say, a few milliseconds or hundreds of microseconds will need to go and scan the sensors. So you issue the reserved address, you go into I3C mode, and then using a series of repeated start, you scan all the sensors that you need to read. This is a feature you don't need to go to stop, and you just go repeated start, address the first sensor, read the data. Notice that now the acknowledge after the data, it's what's called the T-bit. It's actually done in push-pull, and it has different meaning depending on the function of the bus. So in this case, the T-bit will be just the parity of the data. So this gives some protection. I know parity is not the highest protection data, but it gives some protection of the data integrity. And you scan in sequence, so very efficiently, all the sensors you need to read. And then at the end, you will issue the enter activity state. This was also shown by Tim before, where you say, okay, now we go back to rest. So the whole sequence is repeated. It's very, very efficient. Wake up, scan all the data, go back to sleep. And it's very, very efficient and it's quite common thing that's happening in IoT products, especially when you have like inertial motion units, this kind of devices that you are continuously doing this job. There are some of the sensors, they don't have necessarily. Sometimes you have some more data, not 8 bits or 16 bits and so on. So if you have I would say, a significant more, not a whole lot, but some more data to send, it might be worth to use one of the high data rates provided by I3C. Here in the example, you should enter the high data rate 0, which is the double data rate. In this case, you send the data twice the speed. The formatting, it's a bit more complicated because now the header is not just a single address, but it's a 20-bit sequence. You have some preamble bits, some parity bits. Same for the data. But one nice thing about the high data rates is that the data, in addition to the parity, there is also a CRC, 5-bit CRC, which is much stronger. So if your goal is that it's good power, fast mode, but also protection of the data, I think this is also an excellent choice, to exploit the fact that in high data rate modes, you also have a CRC to make sure that the data you're reading has not been corrupted. And the sequence will be more or less the same, other than all these details about the high data rate. You just scan all the sensors. Here you don't have T-bits anymore, but to separate the different readings, there is a hardware pattern. It's HDR restart. It means you can change now the target to a new one, read the new one, and then at the end there is a specific hardware pattern. Usually these patterns you will find using. There is also another example later on for the target reset, where you hold the SCL line low and then you toggle the SDA line a number of times. And then you go back to sleep with you entering, you exit the HDR mode, you go to standard mode, and then you go to put the bus also again in lower, in idle mode. So this is also an additional way to achieve the same thing with faster speed and more data protection. So this concludes the first example. I hope I was able to give the main features of the specification, how they can help to build things. I would like to now to look into another example. There is a feature in I3C, a hot join, that is designed to allow a device to join the bus at a later time. So usually after power up, there is a certain activity of bus initialization, mostly the address assignment, the dynamic address assignment. So in order for a new device to come in, there is a procedure that it can join. It can notify it wishes to join the bus, and then certain things happen. This feature can also be sort of used to selectively power on and off a part of the system. Here, let's say the example here, let's say a typical an IoT device, you have some reading that you're collecting over the day, for example, and then on a periodic base, you wish to send out this data. This can be, I don't know, a smart meter, some field device. Sending can be once a day, every hour or so. So there is no point in keeping the communication unit alive during that. Even if in a low power mode, sometimes as we say, in IoT, you have a battery operator, not rechargeable. So every electron counts there. So you just switch it off, maybe with some application command, but then you need to wake it up. So in that sense, I3C does not have a specific feature there. So this has to be designed at the system level. Can be an external signal, but there is, as I mentioned there is one of these hardware patterns, target reset action, that can be used to really issue a hard reset on the community and wake it up. So the target reset, it's similar to the HDR, but now the number of toggles it's higher. You need to toggle 14 times the SDA line, and there is really a few gates to implement that and generate the hard reset. And this will be only recognized, because this command, it says on which target is going. So the other targets will ignore it. Of course, the one that's sleeping does not know it's going to it, but it will be the only one responding, and so it wakes up. So after it wakes up, it will issue the adjoin sequence. The adjoin, it's really a special case for inbound interrupts. So the way the inbound interrupt and the adjoin works is that the SDA line, now it's pulled low by the target. This is one of the very few cases where it's not the controller to pull in the SDA line low. The controller will say, okay, go ahead, put in the SCL line. This is not a full acknowledge, it's just saying go ahead. And then the joining device does not have an address. So there is a reserved address, 02, and this is very high. Actually, it's the highest address, because the address part can be arbitrated. So if some other target is pulling the line low, it will win. But so this is the lowest one, because address 0 is not allowed in I3C, and same for 01. So this is the highest, let's say, inbound interrupt. That flags that it's a hot join request. At this point, the controller acknowledges the request. It might not acknowledge for some other reasons, but in the example here, we're acknowledging, and then initiates the sequence to make the, let's say, the communication unit fully functional. And then when it's up and running, you can give it the data, then it will be sent to the cloud, and then once the data is sent, you can go back to sleep. So and this is the say the second examples I wanted to show how to reuse some of these interesting functions from I3C to improve the energy efficiency, the way you use the power, minimize the power, and so on. So as we said, there is more than that. You just published a white paper related to the topic of power efficiency, where not only the examples that we were explained here today are there, but there is also other examples. So there is the download link. welcome to go to the MIPI website and have a look, where you will find also tons of other material related to the I3C. Okay, there is not only that, but here are some useful links. Specification page for the full I3C, where you need to be member, and the I3C basic, where you just need to register and agree to the MIPI IPR terms. CTS, the Component Test Suite, mentioned by Tim, host controller. There is a very FAQ web divided by topics. Were really hundreds of questions and cases, that really you can find answers that, that because specification tends to be quite formal sometimes, so sometimes it's a more colloquial way to explain things. Link to the IoT and some reference on other I3C implementation. He also encourage you to get involved. Get involved by participating to the work group, contributing, or if you don't feel, just listening and be there and learning. This is okay. For the groups that there are, we talked today, we have the I3C working group that meets weekly on Wednesdays at 8 a.m. Pacific time. The IoT interest group, it's a group that is not developing specification, but rather taking MIPI specification and see how the best to apply in the IoT space. The group meets monthly, every second Thursday. There are the emails for members and non-members for contact and the link. And with that, I think we have concluded our presentation, and we are now in the question and answer sessions. Please, if you have a question, type them in the chat, and we'll be happy to answer.
Yes, feel free, everyone, to raise your questions. You can pose the questions in the Q&A panel. I do see that a question did come in just a moment ago.
Question, yeah. Question is, let me read it. Hello, can you tell me the latest status on Slimbus? When it was developed, it was some kind of upgrade of I2C. I don't know whether, Tim, I don't know the latest is on the Slimbus, but it's not, I would say, strictly related to I3C. We'll
Yeah, I don't know much about Slimbus, so I'm not going to be too helpful there.
Yeah. We do have a second question. Is there scope for I3C use with future digital microphones? Well, in me, I don't know whether, Tim, you want to take it.
Oh, go ahead.
Start. Yeah. Well, first, let me say that in MIPI we have audio specification. They are specifically dealing with the audio, because in audio there is not just the digital samples, but it's also synchronization among multiple sources, different channels, and so on and so forth. Let's say more specific audio application, probably those are a better fit. However, given the fairly high data rate, I mean, compared to audio of the I3C, it's not in the plan currently, but I think it's personally, I find that maybe it's a nice, let's say, challenge to the group of whether I3C could use some, the I3C features could fit also to transfer digital audio data.
Yeah, I would say, one of the things we're working on with I3C is making sure we're adaptable to what the industry wants. And so, if people come and they say they want, digital microphones over I3C, We've got a very active working group. We're currently working on ways to better expand I3C, and I don't see anything that would keep us from doing that. It's just, like Michele said, it's not currently in the plans, but certainly no limitations.
Okay. Yeah. Yeah. Also, the one feature in I3C is the synchronization of data. You can synchronize the data acquisition from different sources. So maybe something this could be looked into, whether it can be doubled up as audio digital samples. Okay. So I see another question. Is the M lane CCC transmitted just before it corresponding mode frame? So whether the CCCM lane is transmitted before entering into the different speed range. This is, yeah.
That's a good question. I can't remember the exact sequencing off the top of my head.
Yeah, the different, okay, not all CCC are can be done in when you are in a high data rate mode. But the I would tend to say I'm also not 100% sure. I think it's transmitted before, but we need to double check. And then for sure in the specification, there is in the high data rate section is listed clearly which CCC can be transmitted during the high data rate mode, and which some do not make sense there, some are just not possible. So there is a section in the specification and one can look it up. But I think the multiple lane is it's external, but I will not bet on it. Why do the SCL remains at low state during the HDR mode? SCL does not stay low. Perhaps in the example it looked like that, but it's it stays low only when in generating this pattern. In the examples I showed, there were some hardware patterns like HDR restart, HDR exit, target reset, and these are specific hardware patterns where the SCL is kept low. But in general, when you're transmitting data in HDR mode, the SCL does not remain low. Actually, in the double data rate, it's toggling the data bits on every edge, so raising edge, falling edge. When do we expect to see sensors with I3C in the market? As far as I know, there are already sensors with I3C.
Yeah, absolutely. One of the leading ones would be DDR memory with the SPD bus. Is already in the market, but the I3C is starting to hit the market. It hasn't taken its full share yet, I wouldn't believe, but we're starting to see those sensors come. And on top of that, that might be a good point to chime in. We have interoperability workshops that we do with MIPI that allow people to come in and take their prototypes, what they're working on, to come in and test them with other developers. We've actually just opened those up publicly, so it's no longer for members only. This was really created to kind of help support the I3C basic ecosystem as well too. And so if you're in development, if you want to come and try out your device with others, I would absolutely look into going to the website. I think we even have some resources on this presentation, but check out the interoperability workshops. They can be very helpful for developers as well too.
Yeah, actually, let me flash the next slide because these are the next events.
There we go.
And I don't mean to cut off people. I just want to show that we have the date for the interop workshop that is here. It's open to non-members. Okay, we need to to say what you are presenting. There's a committee that will approve. Usually the interrupts are open to members only, but it was decided also to open up to the community, provided that there will be some, it's approved by the committee. There's an NDA to be signed, but nevertheless, this promises to be a very interesting interrupt workshop. It's happening in Germany, Munich, in middle of June. Which information does the target return during an I3C private read operation? Because in I3C, the master specifies slave address and also in a register address. But I saw that there is not register address in I3C read operation. Could be. I don't know. I could try. Maybe, Tim, you can add something if you feel. Normally, okay. In I3C, the address is assigned dynamically, and then one of the transactions is that you issue the dynamic address to the target, and this is selected as a private read. So in that sense, this is analogous to I2C, except that in I2C this is a static address, and in I2C you need to assign dynamically to the target, but it would work basically the same way. And that's the specification. This is listed as a private read. The difference comes after, because you would read the data, but instead of acknowledging each byte, here you have the T-bit that in the read mode is a slightly different behavior than the write mode. And but other than that, I would say it's fairly similar. The controller sends in which register it wants to read from the target, meaning in the private read, this is, you also want to specify something internal to the target, if I understood correctly the question. I think this is because we expect the I3C targets to be more sophisticated than I2C. Let's remember, I2C was a technology was developed in the 80s. This is left really to the application. So in case of let's say serial E-square prom, they will be analogous. So after the address, this is the I3C address, not the internal address of the memory. So this would need to be in the data that you send, but this is application dependent. So it does not go that far, the I3C, because as I said, the devices are more sophisticated now than just very simple serial memory. I don't know what the team you wanted to add. I think, yeah, I got the answer.
I think you got it.
Okay. To me, the main difference between I2C, SPI, and I3C is that those were, in some cases, good performance. When in SPI, they can have a fairly good performance in terms of data transfer. But it's pure hardware. With I3C, you get a higher level of sophistication. You can dynamically organize your addresses. You can have, it's more sophisticated. There is more system level features that you don't find in the other buses. You have routing functions, bridges, device. So it's introducing a new level of sophistication, which is, I think it's more appropriate for these times. In the meanwhile, I think we received one question. Can the primary to secondary master exchange happen often, or does the spec expect to be very infrequent? As far as I know, there's no how often this can happen in the spec. It's just a sequence that happens, and I think one is free to do as much as necessary and without affecting the overall system performance. I don't know,
Yeah,
Tim, whether...
I would agree. I think as we were designing it, we didn't expect anything to happen too frequently, but I would definitely say the spec doesn't limit it. So as you're able to exchange the primary to secondary as often as the spec allows within the structure that's completed. And I think it's kind of implementation specific on how frequent you would need to do that.
Okay, well, thanks very much. Appreciate it, and take care, everyone.
Yeah.
Thank you, everyone.
Thank you. Thanks to the attendees. Bye.